So probability is a very special concept in statistics, and we have sort of their own terminology to describe this concept. So we call, for example, previously we said frequency is describing the how often an outcome occurs. But when we talk about probability, we will say, well, outcome we use event instead of outcome, right, to describe the property of our interest. And so the probability of event, that is how many times or what's the chance for an outcome to be observed, right? That's essentially the same thing. So we'll denote this as the probability of an event represented by x, that is what's the chance of an outcome to be observed, that is it will be the likelihood that this particular outcome or this particular event will occur in a trial, that is in an observation, right, in an observation among all possible outcomes. Well, this is a very sort of obscure definition, but I'm only giving out this definition so that sort of a technical definition of probability. But for the purpose of this class, the bottom line is understand that probability is almost, right, not exactly, but almost the same thing as relative frequency. Okay, so we have the same table. Here we have all the possible outcomes or values or event of this variable, right? With 200 observations or with 200 trials, we can imagine that it's like flipping a coin or throwing a dice, only that this dice has 7 numbers, right? So we can roll a dice and give us a 1. We can roll a dice and give us a 7, right? That is, we roll the dice for 200 times, and how many ones will obtain, right? We're trying this, dice throwing thing activity for 200 times. How many ones do we get? 2. How many twos do we get? 35. All the way, down to 7 or up to 7. And then we can calculate the probability, that is, all the possible, the particular event, right? The likelihood that a particular event, a particular outcome is observed in a trial, right? That is, we throw the dice 200 times relative to or among all the possible outcomes, right? So this is our observed occurrence of an event in a trial of 200 throws. That will give us 0.01, which is exactly how we calculate relative frequency, right? 2 divided by 200, 35 divided by 200, 22 divided by 200, and 30 divided by 200. Okay, all the way to 7 or 19 divided by 200, we'll have 0.095. And if we add up all the probability or all the probabilities, we have 1. And that's a must, right? Because whenever we say that, we have a probability 1 of observing something, that is certainty, right? We're certain that this event will happen. We're not very certain. We're kind of certain, right? It will happen 1/5 of the time, right? So, but then if we add up all the possible outcomes or all the possible events, then of course we're certain that all these value will occur. Okay, so that's the meaning of 1 in the context of probability. Right, so with a sum of all the probabilities, we'll get 1. In other words, right, so all events or all outcomes, right, the probability of observing all possible events in a trial, throwing, a dice however many times, right, will be 1. So, probability is used in describing all kinds of distributions. And in this particular class, we'll be focusing on a particular type of distribution, and we'll call that normal distribution. And normal distribution is sort of discovered by a German statistician called Gauss, right? You might have already heard about him in your high school math class. But anyway, so that's what we also call normal distribution a Gaussian distribution. So Gaussian distribution is essentially a bell-shaped curve. So on the x-axis, we have values or the possible event of a trial, right? But in most cases, we say, well, x-axis denotes the value of a variable, and y-axis is the probability of x to be observed, right? So x-axis, the values of a variable from 1, for example, to 7, and y-axis denotes the probability that we'll observe 1, the probability of observe 2, all the way to the probability of observing 7. Okay, so there are certain properties about normal distribution. First of all, normal distributions are completely defined by its mean and standard deviation. That means once we know the mean and the standard deviation of a Gaussian or normal distribution, we know how it's shaped, right? It might be a little wider, it might be a little shifted to the right, shifted to the left, but once we know these two values, we can determine how it exactly look like. Okay, and that means there are more than one normal distributions, and of course each of them will be defined or described by a different set of mean and standard deviation. Normal distributions, as we have already mentioned, is perfectly symmetrical. That is, if we impose a center line and if we fold this side of the graph to this side, the two sides will completely overlap, right? Pose a center line, well, not very center, but you know what I mean. So if we flip this side over to this side, the two parts will completely overlap. Okay? And then the next property we also have discussed is, with the most typical values, the value that describe, that occur most often, right? That is with higher probabilities are clustered around the center, right? That's why this part is higher, right? Or the area under this curve is larger, whereas the extreme values at the tails, right? There's one tail, the second tail, and this part represents the probability of observing very low values, and this part represents the probability of observing very high values. Okay, so the total area under this curve is 1, right? So for any given normal distribution, the area under the curve, right? So the shaded part, so anything that's beneath this curved line, right, or between this curved line and the x-axis will be the area under this curve, right? Area under this curve. So the total area under this curve, or between this curve and the x-axis, is 1, because that would describe all the probabilities, or that would describe the probabilities of observing all the possible values represented by the x-axis. And we just noted that for any given distribution, if we are able to calculate the probabilities for all possible values, the sum of all the probabilities must be equal to 1, because it is certain that we'll observe all different possible values. Okay, so that's why the area under this curve or between this curve and the axis is 1. And this is a very, very important property that we'll use for later on. Okay? Okay, so Here's a question for you. That is, imagine this is all these seven values. We can imagine that these values are from a 7-point scale, right? From 1 to 7. Uh, Imagine that all these values, follow a normal distribution, right? On the x-axis, and on the y-axis, we have the probability of observing all these possible values. So from 0, that is, it's almost impossible to observe a certain value, to 1, that is, it's almost certain to observe a certain value. So that's probability on the y-axis. So let me ask you, what is the probability of observing a value 4? It seems pretty straightforward, right? You say, if this y-axis plots the distribution or the probability, then what we can do is we'll first draw a line, right? A vertical line so that it would touch 4 at this end, and it would it will intersect with this curve at the other end. And right at the point of intersection, we draw a horizontal line, right, parallel to the x-axis, and make this line to intersect with the y-axis. And this intersection point will be, or should be, the probability of observing 4. So if we sort of say, well, here is about 1, then by eyeballing, it will say, here is about zero point 0.8. Well, not precise, but definitely between 0.7 and zero point 0.9, so we'll say it's 0.8. So you will say, aha, the probability given this distribution of observing 4, right, is about 0.8. Wrong. Okay. This is the wrong way of figuring out the probability of observing a particular value from not just normal distribution, but any continuous distribution, right? This is a continuous distribution. It's not a bar chart, right? So we assume that these values are continuous. Then you may ask, oh, then what is the correct answer, right? It's not about, the precision of eyeballing. I'm not saying that it's not 0.08, rather it's point, 78, right? That's not about the precision. It's not a matter of precision, but this method, this way of finding out probabilities under a continuous distribution is fundamentally incorrect, right? So the correct answer for this question is actually 0, or technically almost 0, infinitely close to 0, right? That's the answer. You may say, well, how come? It can be because you might say that, a very large value is close to 0, probably finding a very large or very small value 0. There's no way that, finding a value of 4 is 0, because you do have a height, right? You do have a difference, for example, between this point and this point, right? It can be. Well, it actually is. It actually is, right? Here's, a little bit of counterintuitive, and hopefully I can explain this to you with a non-mathematical method. Okay, but first of all, let's sort of accept this conclusion. That is, with a normal distribution, right? This is a normal distribution. With a normal distribution of a truly continuous variable. So here we're assuming that these 7 points form a continuous sort of scale, right? But when we say a truly continuous variable, what are some examples that come to mind? We can have time, right? That's a truly continuous variable. Well, I mean, we can of course chop time up into days and weeks, but technically it's flowing, right? So this particular moment is definitely moving, right, in a very continuous sense from the previous moment. Or temperature, that's definitely a continuous variable. And there are many other examples, right? Age, for example, money, right? Income, for example, right? Height, weight, right? So those, with a truly normal, with a truly continuous variable, and if this variable is normally distributed, then the probability of observing an exact value, for example, 4 precisely, right, is very, very, very small. So small that we can regard it as 0. Okay? So here's why. So, if you understand integrals and differentials, you will very soon to see the reason why. But I assume that most of us here are not very familiar with integrals and differentials, so that's why I used a non-mathematical explanation, trying to make sense of this particular conclusion, right? So imagine that we're measuring the volume of rainfall in this particular city, or monthly volume, okay? So immediately you will see that the volume of rainfall is a truly continuous variable, right? It's measured in, I don't know, squared inch, for example, right? And that is a continuous variable without any dispute. So from public data, I sort of gathered these two numbers, the range, right? The average monthly volume of rainfall in Honolulu is from 0.11 to 16.9 inches. I should say cubic inches, right? According to public data. But anyway, right? This is just to illustrate that it is the truly continuous variable. Um, Now let's say, I don't even have to assume that the volume, right, of rainfall follows a normal distribution. That doesn't matter actually. As I said actually, the rule that we just said, right, the probability of obtaining a precise value is very close to 0 actually applies beyond normal distributions. It applies to all kinds of continuous distributions, Poisson distributions, t distributions, f distributions, chi-square distributions, whatever, right? As long as a continuous distribution. But anyway, okay. So that's why I didn't say that. We assume that it's a normal or a distribution or other kinds of distribution. But my question here is because our focus is to find out or is to reason through why the probability of obtaining a precise value from a continuous variable is close to 0. So here the question is, what is the chance of obtaining exactly 5 inches of rainfall, right? So note, exactly 5, right? That means I'm not saying that I want to know the probability of observing 4.999999 inches or 5.00001 inches, right? I want exactly 5 inches, right? I want to know the probability of observing 5 exact inches. If your boss gives you this task, right, to measure 5 inches of rainfall exactly, not 4.9999 nor 5.0001, your boss has given you a mission impossible, right? Because we know that given our, measurement, or the typical way that we measure stuff, it's practically impossible to obtain an exact amount of volume or length or weight or whatever property that they can think of, and not, you know, uh, uh, 1 unit more or 1 unit less. Okay, so that means the probability of observing an exact value is very, very small, extremely small, so small that we can comfortably assume that it is 0. Okay, so that's why, as we said, given a truly continuous variable, right, the probability of observing an exact value is also close to 0, right? Because we cannot even obtain a exact value from a sample or probability distribution, then the probability of observing it by extension, by logical extension, right, is also gonna be very, very small. Okay, so I hope this makes sense and can convince you that the probability of observing an exact value from a continuous distribution is close to zero. Okay, but having said that, right, still we would like to know what's the probability of finding a given value, because that still will give us information, very useful information. It's just that, the previous example only says it is not correct, right? It is not correct to find out the probability of a particular value using this kind of method, right? So that suggests the height, right? The height of a curve is actually not the probability of observing a particular value here, right? The value x. So the height of the distribution actually is not what we should be looking for. But then you may ask, well, then what should we be looking for, right? So given that it is very difficult to obtain exactly 5 or an exact value, right? It can be anything. It can be 4, it can be 3. So given that it is very difficult to find a probability of finding of a exact value, what we can do then is we relax our requirement and say it's okay that you include some errors there, right? Recall we do talk about measurement errors, right? So anything that's not precise will be considered as error, right? So we're saying here, well, if it is impossible to observe the probability value for an exact value, um, then let's observe the probability or find a probability for a very, very narrow range that contains the value that we're interested in. So here 5, right, is slightly larger than 4.9999, and 5 is slightly smaller than 5.1111. So this range, right, so close, but containing 5, right, can be roughly considered as the probability of observing 5, this particular value. Okay, for the same idea, right, if you want to say, well, what is the probability of observing 4 from a continuous distribution, then what you can do is, instead of finding the probability or p-value for 4 exactly, you can say, well, what's the probability of observing a range of value, right, or an interval of values ranging from 3.9999 to 4.00001. Okay, a very small interval that contains the target value. This, right, finding the probability of this interval is mathematical possible, and there's readily ways to do that. All right.